Inverse functions and relations. Now, when we hear the word inverse, we think of kind of as opposites or undoing one another. Like if we think of 3 and we think of the multiplicative inverse, that would be 1/3. When we multiply them together, we get what's called the identity. Well, the same can be true in functions. So if f of x and g of x are inverses, they undo each other to give the identity. And the identity, when we're talking about these functions, is y equals x. So all the x's are equal to y, and all the y's are equal to x. And this happens when they are composed, so when we take the composition. So when something is an inverse of something else, it undoes it to give the identity. So in this case, if I took f of g of x, if I took the composition, I would get x. And g of f of x would also give me x. When I look at the graph, I can see it's symmetrical about my identity function. So if I were to fold it over, each one of those parts would land on the other side. So also, if you look over here, my y values and x values switch places on the function. They undo each other. So here my intercept, my y-intercept over here is at 0, let's say 10. Over here, 10, 0 is on my graph of my inverse function. If we have two functions and we want to know if they're inverses of each other, we can test it in two ways. We can say algebraically, is f of g of x equal to x if we take the composition of those functions, and g of f of x equals x if both those things are true. We can also look at the graphs and see if they're symmetrical about the line y equals x. So there are two different ways we can do it. Oftentimes it's easy to be sure if you're doing it algebraically because you know for sure if it equals x. A little more difficult to graph, but you can kind of tell whether two functions are inverses of each other. So we're going to check it both ways, both algebraically and we're going to check it graphically. So if f of x is equal to x minus 1 over 2 and g of x is equal to 2x plus 1, I can take the composition of them. Now I need to show that both f of g of x is equal to x and g of f of x is equal to x. So let's first start with f of g of x. So everywhere there's an x, I'm going to substitute in my function g of x. So f of g of x is equal to g of x minus 1 over 2. G of x is the same as 2x plus 1, so I'm going to substitute that value in for g of x. And I could put this in parentheses just to make sure, but I'm not distributing anything. So I have 2x plus 1 minus 1 over 2. I can go ahead and simplify. That's just 2x over 2. And then 2 over 2 is 1, so I have f of g of x is equal to x. And I can do the same thing with g of f of x. In place of x, I'm going to put my function f of x. So I have 2 times f of x plus 1. F of x is x minus 1 over 2. And so I have 2 times the quantity x minus 1 over 2, that all plus 1. So when I'm multiplying here, I have 2 over 2, which gives me a 1. And then I just have x minus 1 plus 1. Minus 1 plus 1 gives me a 0. And I have g of f of x is equal to x. So these functions undo each other to give the identity. Now when graphing them, I can tell that this is going to have a slope of 1/2 and a y-intercept of -1/2. So I can plot that here. I can go ahead and use my slope to graph my next point and then draw a line. That's my f of x. I can also draw my g of x. My slope is 2 and my y-intercept is 1. So I can plot that here. I am going to rise 2 and run 1, and then I can plot that as well. Now notice that here my y-intercept is 0, -1/2. And here my x-intercept is at -1/2, 0. The x's and the y's switched places in my identities. So yes, these are inverses of each other. Let's look at another example. Are these two, h of x and g of x, inverses? So we can go ahead and check this algebraically by finding h of g of x and g of, this should say h of x, and see if it is equal to x. So starting over there, let me find a pen and fix that. So I have h of x is equal to negative 2x plus 3. I'm going to substitute my g of x in for every x. So I have 2 times g of x. Let me just fix this really quick. H. Okay. So I'm going to substitute my g of x in for x, and I have negative 2 times g of x plus 3. G of x is equal to 2x minus 3, so I'm going to take that and put it in for g of x. I put it in parentheses because I'm going to be distributing the negative 2. I have negative 2 times 2x is negative 4x. Negative 2 times negative 3 is plus 6 plus 3. And I'm going to add like terms, and I have g of x is equal to negative 4x plus 9. No, they're not inverses. I actually don't even have to do this. I can already say they are not inverses of each other, but just to show you it's not going to work over here either. I have g of x is equal to 2x minus 3. I want g of h of x. So in place of x, I'm going to put h of x. And so I have 2 times h of x. H of x is just negative 2x plus 3 minus 3. I substitute that in, I distribute the 2, and I have negative 4x plus 6 minus 3. Adding like terms, I have negative 4x plus 3. So if I had started with this one, I would also see that no, they are not inverses of each other. Both of these things have to be true. Now notice h of x is the additive inverse of g of x right here. So I have negative 2x right here, and I have a 2x here, positive 3 and negative 3. So just by switching the signs doesn't mean that they're inverses. You have to actually check that composition. Oh, and if I were to graph them, I can see my line y equals x, and it's obviously not symmetric, which means I couldn't fold it over and have it be the same on that side. In fact, my g of x is all on the right-hand side of my y equals x. So now what if we wanted to find an inverse? So we know how to test whether something is an inverse, but if we are given a function and we want to find an inverse. So say we're given the function y equals 4x. Inverses, in the inverses, the x becomes the y and the y's become the x's. So I can just switch x and y. So here's my original one. Switch my x and y and solve for y. So switch my x and y. Instead of y, here I have an x, and instead of x, here I have a y. And then I'm going to solve for y by dividing both sides by 4. So I have y equals x over 4. If you want to write it so the y is on the other side, you can also say y is equal to x over 4. That's the inverse of my y equals 4x. So switching those x and y's and then solving for y's. Now sometimes you're given in function notation a function f of x, and it said f of x equals 4x, and you want to find the inverse. You can go ahead and write it as y equals 4x, switch your x's and y's and solve for y. And if you were to do that, you'd get back here to y equals x over 4, and you would write it, you would notate it like this. So this is the inverse of f of x. That's what that little negative 1 means, is x over 4. So this is f inverse. Now, it's tricky because you have some more notation that you're used to seeing. When you see that negative exponent, that probably means to you 1 over something. So if we wanted to put this in the denominator. But that's not what this notation means. This notation just means we're finding the inverse so that when we compose the two, we're going to get x. So f inverse is not the same as 1 over f of x. Not the same. So you can't just put 1 over 4x. And you can see that that would be a very different function and would not be an inverse. So let's do another example. Sometimes the inverse of a function is not a function itself. So it can start off as a function, and then if we find the inverse is not a function. When something's not a function and it's still related to each other, the x's and y's are related, it's called a relation. So let's say we're given y equals x squared plus 1. This is a parabola. Its y-intercept is 1, looks like this. 0, 1 is the y-intercept. And then if we want to find the inverse, we switch the x's and y's. So instead of a y here, I put an x, and instead of an x squared here, I have a y squared plus 1. And then I'm going to solve for y. Now I know just by looking at this is a sideways parabola. So I have a parabola opening to the right And right here, my x-intercept is going to be at 1, 0. Moves to the right, 1 right here. And so I know it looks like this. But if I want to find my relation, I want to solve for y. So subtract 1 from both sides. Otherwise, I won't be able to take the composition. Subtract 1 from both sides. I have x minus 1 is equal to y squared. Go ahead and take the square root of both sides. That gives me a plus and minus square root of x minus 1 is equal to y. And if you like to write it with the y on the other side, y equals plus and minus the square root of x minus 1. Now, if you were to graph plus the square root of x minus 1 and minus the square root of x minus 1, you would get this same sideways parabola. Now, this is not a function because for a value of x, I'm going to get out 2 values for y. And that's the definition of not being a function. You can also, maybe you've learned the vertical line test. And so that vertical line test is also telling you the same thing, that if I choose a value for x, I'm going to get more than 1 value for y. However, our original one is a function. For every value of x, I only have 1 value for y. Okay, so if we want to find the inverse of a set of points instead of a line or a parabola and determine if it's a function. So if we have these set of points, 1, 2, 3, we've got 4 points, and we could pull out all of those on a graph and then do the y equals x and see if we could find the inverse. But when we find the inverse of a function or of a relation, we're just switching the x's and the y's with each other, because when we compose them, we want to get back to that identity. So let's first look at what we're given. Say we're given these blue points right here. These blue points, I can tell, are already not a function. And the way I can tell that is for my value of x equals -1, I'm going to end up with 2 different y values. I have a -2 and a 4 when x is equal to -1. But let's see if maybe the inverse is a function. So switching the x's and the y's, so -2, -1, just switching those around, switching here, and switching here. Now let's look to see if this is a function. So I have -2, -1, also when x is equal to -2, y is equal to -3. So it is not a function because there are, for -2, for my x value of -2, I have more than 1 y. I have both -1 and 3. And if I plot that, I can see that clearly. So the green dots right here represent the inverse. And if I were to draw a vertical line right here for my value of x equals -2, I get 2 values for y. And now I plotted these just so you could see how they would look in relation to my line y equals x. So they're just opposite of each other on that line. You could fold it over and you would hit this other side. And so my inverse and my original relation is symmetric about the line y equals x. But it is not a function. So the first one's not a function, and my original one is a relation. It's also not a function. But they are inverses of each other.